Listo, doctor. Si gusta, puede empezar, por favor.
Bueno, pues muy buenos días a todos. A nombre del Instituto de Investigaciones en Materiales, les extiendo la más cordial bienvenida a este simposio de estudiantes del capítulo estudiantil de la Sociedad Mexicana de Materiales. A mí me da mucho gusto ver que este capítulo se ha mantenido de una forma vigente, muy proactiva, con mucha iniciativa para, a pesar de las circunstancias, llevar adelante este evento. Desde el año pasado que iniciamos con este problema de la pandemia en todo el mundo, el comité organizador de ese entonces no se dio a la tarea de cruzarse de manos, al contrario, organizaron el evento de forma virtual y tengo entendido que fue muy exitoso, y para este año pues me permití sugerirles que lo repitieran en el mismo formato para no estar supeditados a lo que suceda o no suceda dentro de los parámetros epidemiológicos y de semáforo y de asistencia, etc. Entonces creo que estos formatos, a pesar de ser virtuales y de provocar cierta variante en cuanto a la forma en que interactuamos académicamente en este tipo de eventos, tienen la enorme ventaja de que pues, nos podemos conectar muchas personas sin necesidad de desplazarnos como nos gustaría. No digo que es lo ideal, pero en estos momentos creo que es una forma adecuada de llevar adelante los eventos y las formas de dar a conocer nuestro trabajo, que es el propósito de todo simposio. Lo importante es, sin duda, y eso les pido y les extiendo mi más cordial felicitación, en primer lugar al comité organizador, como ya lo mencioné, por seguir adelante con esta importantísima iniciativa como parte de las actividades de este capítulo estudiantil. Y para todos los participantes, pues les deseo que tengan la oportunidad, con mucho éxito, de intercambiar y de comentar sus resultados con otros estudiantes, con otros académicos inclusive, de manera que ustedes puedan darse un panorama un poco más amplio de dónde están haciendo sus investigaciones en el marco de temas más generales, lo cual sin duda reditúa en la formación que ustedes están teniendo como estudiantes de posgrado y como futuros académicos o investigadores en los que se desenvolverán de acuerdo a sus propias circunstancias y decisiones. Así que no me resta más que desearles un evento muy exitoso, muy fructífero para todos y cada uno de ustedes, que tengan la oportunidad de interactuar con sus compañeros, con académicos, con los invitados que tengan. Y una vez más, mi reconocimiento a este tipo de actividades que sin duda le dan vigor a nuestra vida académica. A pesar de las circunstancias, la universidad sigue trabajando. Tenemos problemas, por supuesto, no lo vamos a negar, pero en medio de todas estas dificultades y en medio de toda esta incertidumbre que nos provocan las circunstancias en las que nos tocó vivir, este tipo de eventos da una luz muy clara sobre la importancia de las actividades que llevamos a cabo. Ante todo, en la universidad, la academia sigue y este tipo de eventos nos dan un claro ejemplo de ello. Así que mis felicitaciones a todos ustedes por su participación, mis mejores deseos de éxito y que sea muy fructífero para todos y cada uno de ustedes como participantes, como organizadores. Muchas felicidades y que tengan un excelente evento. Gracias por la invitación también a estar aquí. El Instituto de Investigaciones en Materia les abre las puertas y les brinda el apoyo que requieren para llevar a cabo este importante evento. Muchas felicidades y mucho éxito en este evento. Gracias. Gracias a Sara y al comité por la invitación.
Pues, muchas gracias. Buenos días y bueno, muchas gracias al doctor Betancourt y a ustedes por su presencia. Mi nombre es Sara Elizabeth Pérez Figueroa, actual presidenta del capítulo estudiantil que se encuentra afiliado a la Sociedad Mexicana de Materiales y a la Materials Research Society. Dicho capítulo tiene sede en el Instituto de Investigaciones en Materiales. De nueva cuenta, me gustaría que me permitieran agradecerle al doctor Israel Betancourt las palabras de bienvenida. Asimismo, quisiera también agradecer en nombre de todo el capítulo por todo el apoyo brindado, no solo para la realización de este evento, sino para las actividades que el capítulo realiza. El capítulo estudiantil trae para ustedes la 9ª edición del Simposio Anual de Estudiantes. Presentamos este evento con mucho entusiasmo y orgullo, como resultado de un gran esfuerzo de un gran equipo de trabajo. Esperamos lo disfruten. Los objetivos principales del simposio son brindar un foro abierto y gratuito para que nuestra comunidad pueda presentar sus trabajos de investigación. Asimismo, que este espacio pueda servir para que los estudiantes puedan obtener nuevos conocimientos y experiencias. Y así como, y hasta colaboraciones con nuevos laboratorios y grupos de investigación. Esperamos que esta edición sea muy fructífera para todos nuestros participantes. Me gustaría agradecer a todas las personas que han contribuido, no solo con trabajo o con apoyo técnico, sino también con ideas. Todo este evento sin ellos no hubiera sido posible. Somos afortunados de haber recibido y de seguir recibiendo mucho apoyo. Mencionar a todos y cada uno de ustedes sería una tarea imposible. Sin embargo, voy a intentar mencionar la gran mayoría y me disculpo de antemano si paso por alto algún detalle. Voy a empezar agradeciendo al Comité Ejecutivo Estudiantil, a Miguel Ángel Peña, que es el presidente del capítulo, a Brandon Ortiz Casas, quien es el secretario del capítulo, a Eric Ulises Rosales Escalante, quien es el tesorero. También me gustaría mencionar y dar un especial agradecimiento al comité organizador, cuyos miembros han ofrecido siempre ideas frescas e innovadoras, así como apoyo incondicional, a Manmohan Jain, a Iván Caleb Ramírez, a David Eduardo Abad, Paula Alexis Merlán, Valeria López, Daniel Navarro, Ana María González y Diego Saavedra. También quisiera extender un profundo agradecimiento al cuerpo técnico del Instituto de Investigaciones en Materiales, quienes nos han permitido contar con las plataformas digitales para ofrecerles hoy y durante toda esta semana nuestro tan esperado evento. Empezamos por Alan Ortega, Omar Alejandro Pompa, Alberto López Vivas. De verdad, muchas gracias por su invaluable apoyo. También me gustaría agradecer a los coordinadores académicos, porque gracias a ellos pues tenemos un gran soporte, ¿no? Al doctor Diego Solís y al doctor Atitot. Asimismo, queremos agradecer a los patrocinadores, quienes nos han permitido poder premiar los trabajos de los estudiantes que se presentarán durante el desarrollo de este evento, al Instituto de Investigaciones en Materiales, a la Sociedad Mexicana de Materiales, a Metales Preciosos de Grado Científico, a la Genoteca, a la Revista de Materiales Avanzados y a la comunidad de Cebiotec. Muchas gracias por sus invaluables apoyos. También me gustaría agradecer a todos los investigadores que muy amablemente donaron su tiempo para participar en este evento y decidieron compartir su conocimiento. Y por último, me gustaría agradecer a todos y a cada uno de ustedes por su valiosa asistencia y participación. De parte de todo el comité organizador, esperamos que encuentren enriquecedor este evento y que realmente lo disfruten. Bienvenidos. Y bueno, con esto marca el inicio del 9º Simposio 2021 y a las 9 tenemos nuestra primera conferencia. Los invitamos a que esperen alrededor de 17 minutos para que podamos tener a nuestro primer ponente. De nueva cuenta quisiera agradecer al doctor Betancourt por el tiempo y por el apoyo y por las palabras. Aplausos virtuales, ya que son de esta manera ahora. Muchas gracias, doctor. Gracias. Y bueno, continuaremos en 17 minutos. 16 minutos continuaremos la transmisión con el primer ponente. Muchas gracias.
Hello, and please welcome Dr. Luis Fernando Velázquez. Their conference is going. Let me tell you about the Dr. Luis Fernando Velázquez. Luis Fernando Velázquez is a principal investigator with the Microsystems Technology Laboratories of the Massachusetts Institute of Technology. He leads the Micro and Nano Enabled Multiply Scaled Down Systems Group, which conducts high electric fluid phenomena and manufacturing applications. His work currently focuses on additively manufactured micro and nano systems. Please give a welcome to Luis Fernando Velázquez Garcia. Doctor, I will remember you that 5 minutes before your conference is over, we will remember you so you can finish your conference. Thank you a lot, and now the talk is up to you.
Okay, thank you, everybody. Can everybody hear me? Like thumbs up? Maybe somebody show me a video. Can you see me? Okay.
Yes, we can.
Okay, so let's get started. I'm going to share my screen. Okay. Everybody should be looking at a white screen. Is that correct? Thumbs up.
Yes.
Everybody?
Yeah.
Okay. Okay. So let's get started. So are we waiting for more people, or that's it?
You can start. Don't worry, Dr. Luis, please. Thank you.
Oh, okay. Well, okay. So I lead a group that conducts research on high electric field phenomena, like the environmental effects that happen in storms, like lightning bolts. In particular, we investigate topics such as ionization, plasmas, X-rays, and in all of them, besides the nature of being high electric field phenomena, we have found that the systems that we put together are very complex because they are described as nonlinear equations and because they require this multi-scale hardware. So there's stuff that happens at the nanoscale, at the microscale, at the mesoscale, and everything has to work together. And in particular, a lot of these devices require some kind of three-dimensional arrangement. So because of that, our research is really based on two key columns. One is what I described about high electric field phenomena, and second is about 3D printing. So it's something that we have been doing for the last 8 years, and we have found that in quite a few cases is the right manufacturing tool to make these advanced devices. So we still do things in the clean room, semiconductor clean room, but where our focus is research-wise for the last 8 years or so is in 3D printing. And it's because 3D printing has this nature of being multi-scale. You print these volume elements called voxels, which are very similar to the picture elements called pixels that you probably are familiar with. And any object that you print possibly is many orders of magnitude smaller than the voxels. So you get this multi-scale nature already inherently, and when you add things, all of the features of 3D printing, then it's a very compelling argument. So we work on all kinds of interesting projects, and I'm going to quickly survey you here on what kind of devices we make. We work on the 4 states of matter, for example, for solids. We make nano-atomically sharp tips that quantum tunnel electrons, and with that, for example, we can create these X-rays that are very special because they can image soft tissue. Your typical X-ray can image only, mostly hard tissue like bones, so it's good to, if you want to know if you broke a bone, but if you want to image soft tissue, you need to use a middleman, for example, iodine. So you need to inject some substance, and based on what you register with the substance, you are going to figure out by association if the soft tissue has any problem. So our X-rays bypass all that and directly can image the soft tissue. Another example is liquids. What you see there is a microencapsulator. So it's a device that generates these core shell particles that are useful for many things. For example, drug delivery, and reinforcement of composites. In particular, you can make the composites self-healing. So imagine that these are little drops of epoxy, and if you bend enough the composite, then it can release the epoxy and heal a crack. The innovation here is that it's the first of its kind, and that let me see somebody. Okay. Oh, so you're saying that so you cannot see the presentation? Is that correct? So
No, we can see it.
Can you see it?
Yeah, we can see it.
Oh,
We can
okay.
see the image of solids, liquids, the image of 3D, and the 4 centimeters bone.
Oh, okay, okay.
So,
No, I don't know.
yes, we can see it.
Okay, I got a chat saying that they couldn't see it. So okay, so let's continue. A third example is gases. Can you see that the gases device is orange?
Yes, we
Yes.
can see it. It's PCBs, ion cage.
Yeah. I don't know. Okay. So maybe there's some technical difficulties somewhere else. For gases, what you see there is an ionizer, is something that produces ions from neutrals. And the key insight here is that our devices work with a lot higher pressure than the state of the art. You typically operate here on the order of 10 to minus 6 torr, so very, very high vacuum. For context, the atmospheric pressure is on the order of 1,000 torr. So we're talking like a very, very small fraction of the original pressure. But our devices can work at very high pressure, and because of that, they are very, very efficient. Continuing, we also have work on plasmas. Plasma is superheated gas to the point that a component is ionized, and it's the most abundant kind of matter in the universe. For example, the sun is made of plasma, but here in Earth, you see it in many cases from fire, some kind of plasma, and in reentry of spacecraft. So one of the things that we do is developing hardware for space applications, and this is an example. So it's a sensor that allows you to characterize this plasma. You can measure properties like the density, the energy of the ions, the potential that they have, etc. So plasmas are very similar to gases, just that they have these add-on properties that are related to how they behave electrically. And the point of the matter is that our devices can create can generate data that is of far better quality than the state of the art, because they are miniaturized. You can measure with a lot more precision and with a lot more signal to noise ratio, whatever you need to measure. Finally, there are examples that are not not directly related to high electric field phenomena, but perhaps they serve a support role. For example, pumps. You need pumps to evacuate gas from, let's say, a container, and some of these devices require vacuum to operate. So what you see there is a positive displacement pump where this piston moves back and forth, and these valves are cycled, and with that, you can create fairly good vacuum. So you see that from atmospheric pressure goes down to 100 torr, so that's a compression ratio of 8 to 1. I need just one stage, which is a lot better than what you can do with any other miniaturized technology. And finally, we really work on all kinds of neat ideas, and what you see there is an example of treeless wood. Tree, as you know, trees, as you know, produce wood, and it's a very slow process. So that if you were going to start by planting the tree, it will take like 20, 30 years just to get a tree, and then you need to cut it, so harvest just a portion of the material. And overall, the system is very inefficient, not only because of the time that I mentioned, but also because it requires some footprint in land. It's sensitive to climate, sensitive to seasons. So overall, it's not like a quite efficient process in terms of what it could be. So we have been working on using cell culture methods and 3D printing to create wood without having to grow trees. So you basically create a composite that is full of cells. And one of the neat things that plant cells have is that they are basically stem cells. So like your typical plant cell can become anything if you send like the right signal. In this case, you have a composite, you have the cells like in their original form. And if you use cues like pH, hormones, you tell the cell to change into wood or change into cellulose. Wood is lignin. And because of that, then you can change the cell to make the cell evolve into whatever you want. And another thing to remember is that wood is not alive. So you can do this process, and the end process of producing wood is that the wood dies and creates this structure based on lignin. So we're looking at all kinds of interesting things, but what I wanted to tell you today is about some of our work in additively manufactured micro and nano system, which has been this exploration of what you can do with non-traditional microfabrication. So I claim 3D printing is microfabrication because the voxels that we manipulate are of the order of tens of microns or less, which is right in the realm of micro and nanotechnology. And we have been one of the groups that started working on this for the last 10 years. So additive manufacturing was going on for quite a while, but it is not until rather recently that it can actually provide solutions for the micro and nano world. What you see here is a summary, a graphic summary of most of the commercial printing technology. You see there's quite a large breadth of what you can do, but there are like a few key ideas. Perhaps you use a liquid that is photopolymerizable, or perhaps it changes phase with temperature, so you extrude it. You can also do material jetting, that in a nutshell is what you do with your inkjet printers. So the inkjet printers spit these droplets of ink and they create the document you want to print, but you can generalize the idea to a 3D volume. You can also inject binder, and that's called binder jetting, or you can directly use lasers to melt the powder bed, etc. So as you see, there are quite a few options, and some of them are related with the actual material you're going to print. So we have been exploring a few of them and also inventing new technologies so that we can print the devices you want. The key idea here is that when you go to the clean room, you are grossly limited and constrained by what can be done there. So the clean room for semiconductors is really meant to make semiconductor chips. And because of that, there are certain materials that you cannot get in, and there's certain segregation, which means we need to keep things isolated. They cannot like mixed. That otherwise you cannot make working CMOS, for example, which is one of the kinds of electronics that you would like to make. What you want at the end is to create the structures that you want with the right shapes and in the materials you want. So if you are going to make a heat exchanger, you need a material that is a very good conductor. But if you want to keep as much as possible the heat of the reaction, then you need to make it in something that is insulating. And the key material for the semiconductor industry is silicon, and silicon is good for certain things and not so good for certain others. So we became like used to using silicon without any major justification, but I think that it doesn't have to be like that. So you need to really match the application to the materials. And then what you win, as I described at the beginning of the talk, is that 3D printing can allow you to make these multi-scale three-dimensional objects. And in quite a few cases, that's what you need. So you still need to go to a clean room for certain things, but for the others, you should explore 3D printing. Other advantages that I would like to mention is that, first of all, you can print-to-print customize. So every single device you print can be quite different. And this is of great advantage, for example, for personalized healthcare. If you are going to replace your hip, you want your hip to actually perfectly match you. You don't want to choose from a catalog with a gazillion sizes, which most likely is not going to fit, and you need to make some adjustments. You want it to fit perfectly the first time. You can make a lot more variation in the geometries than traditional manufacturing. You can reduce the cost if it's a complex enough structure. If you are making something that you can mass produce because it's identical, the design, and maybe you can stamp it or you can inject mold it, then additive manufacturing is not for you. But if you're making something fairly complex because of the shape, because of the materials, then additive manufacturing can actually make it cheaper and faster. And finally, because of this issue that you can produce faster, you can iterate aggressively the designs. So what we have seen in our group is that the papers we publish are exquisitely iterated design. It's not like what you typically happens in the clean room, which you make your best guess at a design, then you make it, and then you get some data, and it has passed so much time, and you have spent so much money that you learn about some issues, but you cannot really address them. You need to go to the next project. In this case, you can aggressively iterate the design and get something that is a lot closer than what you perhaps would like to commercialize. So today we're going to see about 5 different manufacturing methods that have yielded excellent devices, either because they work better than the state of the art or because they didn't even exist before we're able to harness additive manufacturing. And the 5 technologies are electrospray, vat polymerization, extrusion, material jetting, and binder material jetting. And I'm skipping a couple of other key developments just because of time, but we've also worked on microplasmas to create interconnects and electronics, and also in a technique called direct ink writing. And with that, we have done things, very, very interesting things like quantum systems. But I hope that these 5 different technologies gives you an idea of what you can do with additive manufacturing. Let me see. So in terms of electrospray, what we are interested is in having a technology that allows you to create nanostructured imprints. It's a technology that is not commercially available, but that you can easily put together if you have a high voltage source. So if you are not familiar with electrospray, here's a video. So you see it's a capillary, and you see that the meniscus of the liquid evolves from a cone to, from a hemispherical surface to a cone, and then from the tip of the cone, you spray droplets. So what you are not seeing is that I have a counter electrode on top of the capillary, and I'm biasing a voltage. And when the voltage is high enough, then the meniscus does this effect called a Taylor cone. And what we like about this phenomenon is that it produces very uniformly particles. And you can use it, for example, to atomize. Okay, you have an atomizer for liquids. You can also have a combustor. The combustor have an atomizer, and then you have a combustion chamber, so you efficiently extract heat from that combustion. You can also do liquid chromatography, which is a technique, a chemical analytical technique. And as a matter of fact, this was the Nobel Prize in Chemistry in 2002, how to use electrospray to do mass spectrometry of biomarkers. That was John Fenn from Yale University. CubeSat propulsion, so small satellites, and finally nanomanufacturing, particularly imprints. So the best way to think about it right now for electrospray is like a spray can. So, but instead of making like a graffiti on the street, that you're going to use it to make some nanostructure material. The physics are such that electrospray allows you to spray pretty much all kinds of structures depending on the liquid. So you have your spray, you can generate droplets, fibers, or ions, pretty much depending on where you're operating and what's the working liquid. The simplest operation mode would be droplet emission. And in that case, there is a clear correspondence between the current that you emit and the flow rate. And this minimum flow rate is based on the actual liquid that you're pumping. But if you're going to do ions, which is something that, for example, you'll be interested if you're doing space propulsion, then you deal with liquids that are a lot more electrically conductive, and you deal with flow rates that are a lot smaller than what you do with droplet emission. And finally, if you do fiber emission, you're dealing with liquids that are basically mixes of solvents with long chain polymers. And in this effect of producing the jet, so like from the cone, you emit a jet and the jet breaks up into droplets, for example. So from that stretching of the liquid, you can actually get fibers, and by hydrodynamically stretching them, you can get down to nanometers. So this is an opportunity to make nanofibers. So you see, it's a very comprehensive method, very simple. And as I say, anybody can put it together if you have a high voltage power supply and some kind of liquid feed, which could be like a syringe pump. So it's not really like high tech, but allows you to make high tech developments. This is an example of what you can do. This is from the group of Rogers in University of Illinois. And the idea here is that you have a plurality of needles that allows you to print whatever you want. And what he did is to explore printing with multicolor. Okay, so can we make an imprint composed of multiple colors and put them together? And he has shown this very, very neat work where, for example, this bird is made of 4 colors, and then you go and print different parts of the parrot with different nozzles. So the idea is that you are dedicating for a given color a given nozzle, but you have like this stage so that you can create in an organized way the different features. But the key idea here is that it has great resolution because of the physics of the electrospray. But what this is really telling us is that perhaps we can use this to produce multi-material devices. So instead of having these 4 colors, perhaps we can think of printing something that has conductive layers and dielectric layers, semiconducting layers, piezoelectric layers. So we're talking right now about making a nanostructure electronics or nanosystems. So this is an idea that people have started to explore. And this is an example of work from South Korea, where without any kind of focusing mechanisms, you can make like fairly narrow features. So this is just a trace of the order of 6 microns. And then when you measure the electrical conductivity, it works very well. You need to anneal it to of the order of 150 Celsius. But after that, the electrical conductivity is pretty much like bulk conductivity for in this case, for silver, which is a very highly conductive material. So what you see here is that electrospray moved from being able to make complex pictures to actually make something useful. So right now, this is something that could be used for interconnects, or this is something that can be used for routing signals to whatever electronics you have. And this is made at room temperature, except the part of the annealing of the film, of course. So this is really exciting. And again, it's just spraying these nanoparticles, and you can do these long and narrow features because you can operate it at close proximity, which is called near field electrospray. But what my group has been doing is, instead of working in those topics, is working in transducers. So transducer is a device that interfaces between two energy domains. For example, you have some chemical phenomena and you want to measure it, and then you get an electrical signal. And what I just described is a chemical sensor. But for example, you want to transition from an electrical signal into movement, mechanical movement, and that's a possibility for piezoelectric actuation. So transduction is very important to us because it's what enables us to take the realm of electronics into the whole universe and all the possibilities of the different kinds of energies that you can encounter. So in our case, we have done things like this. So this is a conductometric sensor. So the sensing part is this dot, and this is a four-terminal device. If you are familiar with electronics, you know that this is a fairly common structure that you use to measure the electrical properties of a material. For example, you can put a voltage and measure a current, or the opposite, and based on that, you can see if there are changes in the resistance of the film because of some stimulus, for example, the chemical presence of a compound. And the printed part is zoomed here as an atomic force microscope. You see, it's made of flakes of graphene oxide, which is a 2D material that is a semiconductor. And what it's important to understand is that typically semiconductors have conductometric behavior. So they get some stimulus and they change resistance. And then you can measure that change, and based on that, you can infer the quantity of the chemical stimulus that they received. With that, we have been able to create sensors as thin as 20 nanometers. So these imprints are made of flakes, graphene oxide flakes, and the pile of flakes is thinner than 20 nanometers. That's like crazy. To give you an idea, the diameter of one of your hairs is 100 microns. So we're talking that is something that is like 1,000 times smaller than the diameter of that. So this is smaller than cells, etc. So your typical cell, well, there's a wide variation, but it's on the order of 10 microns of that order. So this is really, really small. But I think what is really important is that even though it's a low-cost technology, you can make something that is actually useful. And what you see here is the data of how the resistance changes versus time. So it's a dynamic response. We put the sensor in an environmental chamber that allows us to change the humidity, and you can relate the electrical resistance change to the humidity that you have there, okay? And what you see is that there are two data sets where the two sensors very closely follow. The insight here is that one sensor is our printed sensor, which is cents of dollar and takes, I don't know, 10 minutes to make, versus the other sensor, which is a commercial sensor by a major vendor, Honeywell, and that has been NIST calibrated and all this. And it is a sensor that costs hundreds of dollars. So you see that paying this extra money is not really giving you anything. As a matter of fact, our sensor is more sensitive. So like our sensor is the one that jitters around, and it's because the Honeywell sensor has these integrators to try to like smooth out the curve. But what you're getting here is that additive manufacturing can actually help you make better systems. So this is not like a poor man's version of the sensor, or because I don't have access to a clean room, I'm going to create this second-class sensor and see what I can do with it. This is not the case. It's like it's a sensor that works as well, if not better, as whatever you can put together in the semiconductor clean room, and that happens to be made with a technology that's accessible. So I remember somebody, so I get people to visit my lab to do research, and some of them are from Mexico, and they keep looking at what we do and they duplicate it, and that's great because it's really a technology that is going to democratize high tech. So if you want to put together a clean room, it costs like hundreds of millions of dollars, and very few institutions can actually do that. But if you tap on additive manufacturing, then I think like the energy barrier of how expensive it is to do high tech is going to lower, and this is just one of the examples. So let's continue and talk about another possibility that we have done in our lab, and it's piezoelectric. So I mentioned that there's a transduction between mechanical and electrical. If you have a quartz watch, that's what it does. So it has like a crystal that oscillates because of this electrical signal, and you can use that, for example, as a source of frequency or source of time. But in order for that to be efficient, you need like specialized manufacturing and also very pure material. So that crystal, quartz crystal, is a single crystal. So there's a lot of people that have tried to do piezoelectrics that are printed, but they tend to be lousy because the quality of the material is not good. But what we have seen is that if you harness this technology, electrospray, that is not true. What you see here is something we published a couple of years ago, where because of this near field electrospray, you're able to make these very well-defined traces. Those traces are made of zinc oxide nanoparticles, and zinc oxide is a piezoelectric. And with this, we're able to make strips that are like 200 microns of width without any masking, without any of that, and are as thin as 53 nanometers. Again, like we're talking really nano stuff that is done with a low-cost system. But I think what is most important is that you can actually make resonators. So I'm not a resonator expert, but many people are, and that's the heart of many of the exciting high-tech applications that we have. For example, we use resonators for inertial navigation. So the accelerometers, the gyros, those are resonators, or time sources. If you want to tune the signal of a cell phone, the circuit actually uses some kind of resonance structure. And that operates in gigahertz. So the question is, can this be useful for such application? And the answer is yes. Like, for example, you can create this structure where you start with a flexible substrate like PET, that's a plastic. Then you can buy it already spotted with ITO, or you can spotter yourself. But then you electrospray your film. So you can use these traces and weave them, so like overlap them, so that you create an area. And then you close everything with conductive tape, or if you want to use, for example, you can also spray these silver particles that we talked about. And here is your bulk acoustic resonator. And with that, you can characterize it. There are all these instruments that can do it, and it's really neat. What I'm showing here is the reflection coefficient, and there are 3 other coefficients for when you operate with RF. But the key insight is here that you can see this sudden change that is calling about the resonance about 5 gigahertz. So what we're talking about is that using fairly inexpensive hardware, you can create devices at room temperature that oscillate at 5 gigahertz, which is a lot faster than anything you can print. And what it's telling us is that the material you print, because it's electrosprayed and because it's so thin and all that, is of the greatest quality. So you're able to create a resonating structure that has nothing to envy to something that is done in the clean room. So these 2 examples that I gave you gives you a sense of what possibilities would be in electrospray printing. So let's continue, and let's change to a different topic, which is vat polymerization. And in this case, we want to make complex microfluidics. So as you see, it's a video where illustrates what the idea is. So you have a photosensitive resin, and you have a vat, and then you have this piston that goes up and down, and that's in the jargon of printing is called platform. And then you have this way to generate a 2D pattern, either with LEDs or with mirrors or with a laser. And the idea is that every time the piston goes down, a 2D slice gets stuck to it. So by virtue of going back and forth, what you win is creating a 3D structure of something that is made of polymer. And we got excited about that because now you can get low-cost printers. Now it's like 10 years, since 10 years ago, that have 25 micron voxels. And that's exactly in the realm of microfluidics. So you can do a lot of interesting things with that. In particular, I wanted to show you a couple of examples of what we have done. So this is a nanofiber generator where you cannot see it because it's an opaque resin, but it has a fairly complex network of channels that is supposed to regulate and uniformize the liquid inside. So this is going to use these polymer melts that generate nanofibers. But at the end, if you do well your design, then you get this thing to work uniformly. So what you see is each of the emitter is producing a jet, and those jets is going to get whipped and stretched because of these electrohydrodynamic effects. And if you have turning a rotating drum, then you can collect them aligned. So you can get these striations in the film. And this is something that you can use, for example, for tissue scaffolding. That structure, that pre-ordered structure is actually very good for that. But what it's really interesting for our work is that it's very uniform. So we said that we're firing from a plurality of emitters, but we can also vary the flow rate and look at what happens. Your typical electrospray source doesn't have but one emitter, or if not, it's like this free space thing that is very unreliable. And it has this huge variation in the diameters. So you produce anywhere from 50 nanometers to 500 nanometers. And that's a problem because if you have let's say a filter that has holes of 1 micron and holes of 1 millimeter, well, that's really a filter for 1 millimeter because like the 1 micron particles are going to escape through the 1 millimeter. So you want as compact distribution as possible. And then what you see here that even though we vary twice the value of the flow rate, you get basically the same statistical distribution, which this development is about high throughput production of nanostructures. Another example is microencapsulation. Is something I mentioned at the very beginning. And you see them that they're working uniformly and producing these core shell particles. What I wanted to say here is that you really see them that are uniform because this is a plot of how much current each of the emitters is producing versus the flow rate. And you see that they closely match. So there is this shape that is a square root that is predicted by the physics. But what is important to see that even though you have a wide variation in the number of emitters, the per emitter performance is very similar. So this talks very well about what you can design in these devices. And these devices are the first of its kind. So the hydraulics are so complex that you cannot really efficiently make them in the clean room. We will be talking about many wafers to bond and many layers to transfer, and that would be just cumbersome. But with 3D printing, you can monolithically create this 3D structure, which in this case is these helical channels that makes possible to create the core shell particles. So you can use, for example, the core can be medicine and the shell can be protection for the medicine. So you can ingest those particles and be protected, the cargo, from the digestive system, and then when it gets into the intestines, and then it gets released. And with that, you were able to give the dose, the drug, without having to inject the person or something along the lines. This is also work from other researchers. This is Nordin in Brigham Young University. And I think I'm bringing to this attention to transition to the next topic, which is we were talking about what we can do with 3D printing, and what he has been doing is using this stereolithography to make actuators. So the material is not really meant to be flexible, but it is. And if you design things right, you can make things like a valve. You can make like a membrane that closes and opens. And if you put together a few of them, you can actually move liquid. So this is a good example of a pump that is made with additive manufacturing. It's a fairly complex device. And all what we said still applies. It's a device that is very inexpensive, that would beat performance to whatever you can do in the clean room. So that motivates us to go to extrusion, which is a technology that we have been working to create multi-material objects of the engineering plastics. The plastics that you can process with VAT polymerization are not of the same quality because they have to be photopolymerizable. So you cannot print nylon with VAT polymerization, but you can print nylon with extrusion. And nylon is a very good plastic. So that's what we're going to show here. In a nutshell, it's about rastering an area with a nozzle that is extruding a material that has some molten temperature. So typically you use a thermoplastic, but there are some other possibilities. And at the end, layer by layer, then you create whatever feature you want. And what gets us very excited is that you can use high performance materials like nylon, like PEEK, and that you can actually easily print multi-material because you can have a head of multiple nozzles and each of them prints a material, similarly to what we saw with electrospray, but in this case, extruding material. So with that, we developed a magnetic technology. So what you see there is a printed magnet that is made of nylon, and it's made of these neodymium particles, and it's a very good hard magnet. You see, it can get the remanence of the order of 5 Tesla, which is fairly high. So it's not the highest ever, of course. We cannot put as much microparticles as we would like because otherwise you cannot extrude it. But you can extrude a material that is very decent and very capable as a magnet. And one of the things that we can do is to make an actuator. So we have like a membrane and it's attached a magnet, and then we have a coil, and then by having these magnetic fields acting on the magnet, we can move it. So you can see that the membrane can be actuated like 50 microns, which is adequate for a number of applications. But one of the things that we say is, can we actually do something useful with that? And this is a pump. So it's a magnetic pump where the piston has a magnet, and we have these diffusers that allow us to cycle the liquid without having to resort to valves. So it's a valveless system. And to give you an idea, this is on the order of 1 centimeter. So this design is pretty neat because it's not your typical back and forth positive displacement pump. This is the best way I can describe it. This is like a bell. It goes like this, like back and forth, and that's how you push the material. This is monolithically printed, so there is no assembly. You need to keep rotating the object when you print it, but everything is put monolithically together. The magnet, the piston, the membranes, everything. And it's amazing, but it's straightforward to do with a low-cost printer, and it works very well. Look that if you use it for pumping liquids, it can pump 8 milliliters per minute, which is a lot higher than anything you can do in the clean room, because we are able to process larger pockets and operate at higher frequency. And again, this is nylon. So nylon can withstand all kinds of abuse against something that you can do with material jetting. And if you also use it as a vacuum pump, look, that is fairly decent. You can reduce like a third of the pressure in a matter of seconds. So what you see is that with extrusion, you can put together a multi-material hardware that actually outperforms the state of the art. And as I mentioned, nylon is a very good material. We have actuated these devices for 14, 15 million cycles and show no degradation. And we stopped because there are just so many cycles you can do. So like you can probably run the pump for a year, but we are not really geared for that. But there is no reason to believe that it can go so much more than these 15 million cycles. So you're talking that you can create devices that actually can be deployed, that are not like these curiosities that you see in the lab. And with that, remember that right now what we are describing to you is we are interested in actuation. So we get good quality materials. Can we do more of a long stroke actuation? And that's a good opportunity to introduce material jetting. And it's a technology that on paper sounds so complicated that you say that will never work, but it's actually one of the most successful printer technologies that there is. For example, the Stratasys printers. And all what it is an inkjet head that has a lamp and a roll associated to it. So you print your layers the way you print a document with the inkjet. And you have the possibility to print multiple materials because of, because of the each nozzle can be like routed to a different material, okay? And with the light, you solidify it. So it's sort of vat polymerization, but not quite. And with the roll, you planarize it. And again, it sounds like crazy, but yeah, it actually works and works very well. And what we did in particular is positive displacement vacuum pumps. So it's a schematic. You see, you cycle pockets of gas from low pressure to high pressure, okay? And this is a standard technology to create vacuum. But the problem is that if you make a microfabricated version, what kills you is the dead volume. So there is not much difference between the maximum volume that I can actuate and the minimum volume that I can actuate. And it's based on that ratio, how much vacuum I can make with this technology. So people have come with very intricate design. That's a design from Michigan that has many of these actuators, and they cannot get any decent vacuum. So the reality is that these devices don't really do it and have not been ever used in a practical application. So what we did is to come out with a structure that I described at the very beginning, where you have a piston and you have these membranes that you cycle, and with that, you can create very good vacuum. So you can go from 800 torr to 100 torr within a few seconds and maintain it, right? And that's a compression ratio of 8:1. And on top of that, you also move a lot of flow rate. But what is truly amazing is that our devices work better than whatever is commercially available for a comparable size, of course. And what you see here is that if you have a given pressure, our devices can actually move a lot more flow rate. So what you see again is that making hardware via 3D printing, what enables is to make better systems. So there are examples where this doesn't work, of course, but we just choose the examples where it makes sense to 3D print. And we show that because of the performance, it makes sense. Let me shift gears and tell you about the last technology, which is 3D printing using binder material jetting. And the idea is a lot simpler than material jetting. So you have a base material that is a powder, and then you have this inject to spray like glue. It's a glue that eventually you can remove. And the technical term would be binder. And as you print these layers, then you put more material, you planarize it, and then you continue building. So you have the object inside a pool of this powder, and it sounds like it's so crazy that you can actually get something working out of that. But again, it's a technology that has been developed for many years, and it's actually commercial, and it works very well. So you bring the object inside the powder, and then you anneal it and use some of this processing to make it react. And at the end, you can extract that part. So we have been using that technology because is the technology that gives you the best resolution for metal printing of the commercial methods, and that has enough high throughput. So you can do with this technology way better than what you can do with, for example, lasers. And it doesn't have the issues with the thermal gradients and the stresses that you build up because you're melting, remelting, cooling so quickly. So it's a great technology. And what I want to tell you is how this is actually helping us change space. So perhaps you're familiar with CubeSats. They are like miniaturized satellites that are very good to make focus missions. And these devices are really meant to democratize space. So instead of sending a bulky, heavy, and expensive satellite, which can cost like tens of thousands of dollars per pound and hundreds of kilograms, so it's a lot of money. You can send perhaps something on the order of kilograms and liters that does well one thing, and that's the one thing that you care. But the problem with that is that the current CubeSats are made like the way computers used to be made. So I don't know if you're old enough to remember how it was like, but there used to be like a motherboard, and then you put all these cards, and there was this inefficiency in terms of the integration of the different cards. Right now, if you buy like a computer from Apple, everything is like bonded and soldered. So it's a lot better integration, and it's designed actually with whatever electronics you have in mind. So it's not this plug and play. So right now they're doing it plug and play, and it's very inefficient in terms of the mass and the size. And in space, mass is everything. As I say, it's very expensive to do this kind of thing. So our idea is called NewSat, and it's a project that has been going on for a year or so with Portugal, is to create 3D printed versions of this CubeSat. And the example I wanted to bring to your attention is propulsion. Once you're in space, you can do, once you're in orbit, you can do all kinds of things to propel the spacecraft. If you want to take off from ground, you need chemical propulsion. There's not really any other way around right now. But once you're in space, there are better systems to efficiently eject the propellant. And in a nutshell, there is a measure called the specific impulse, which is how efficient I am doing with the propellant. And what you want is high specific impulse. So you see that the other alternatives for miniaturized satellites are less performing than the electrospray. So you can have a lot higher specific impulse and a wide variety of that, and you can deliver some adequate thrust. So if you use chemical propulsion or pressurized gases, yes, you can deliver more thrust, but if the idea is to make the most of the propellant, it's better to trade off time for propellant. So if you use an engine that does chemical propulsion, it can do the maneuver faster, but at the end, it spends more propellant. And one of the very hard things to do in space is to refuel a satellite. So you want to make the most of that propellant. So that's why we got interested in that. And what you see here is the first fully additively manufactured electrospray engine. And this is something we reported in December. So it's a bunch of needles that are 3D printed and in metal, then they are electropolished, and then you grow these zinc oxide nanowires. And the zinc oxide nanowires are going to transport the liquid to emission sites here. So using a bunch of needles, and these holes supply the propellant from the bottom, okay? And they just climb because of capillary effects. And what is really interesting, and they work great and better than the state of the art. So this is how they work, so they glow, and that's pretty cool. This is made in vacuum, but the important part is here. You typically emit a bunch of particles when you do electrospray, but in our case, our devices only emit one, and it's the lightest one. And in both polarities happens that. And what that means for us is that it has the highest specific impulse possible for the propellant. So remember they were saying that we really need to be good about being efficient with the propellant. Well, guess what? The 3D printed devices are the most efficient thrusters you can make. And we still do not know sure why, but we believe that is related to the interaction with the zinc oxide nanowires and the way we transport the liquid. But this is quite repeatable and is really exciting. So, you know, I have made like a big journey through different technologies. So I wanted to finish with in a couple of minutes with what's the future of micro nanosystem manufacturing after you have seen all what I told you. I think additive manufacturing can be used to really do like jazz manufacturing. And if you're familiar with jazz, is these very skilled musicians that they play together something without practicing, like on the go. So this is the kind of freedom that you're going to get with additive manufacturing. In a virtual foundry, without having anything more than feedstock, without stocking parts, without having an inventory of anything but the feedstock, you should be able to make all kinds of complex and not so complex products that satisfy all kinds of needs, from medical to healthcare to energy, cars, airplanes, you name it, where it's going to really democratize technology, because the cost of one of these foundries is going to be a lot less than the current method. And the current method is crazy because it's based on creating the goods in very few places and then transporting them around the world. And if you got addicted to two-day delivery like Amazon, then that's actually part of the problem, because a third of the energy is spent in transportation. A third of the energy in the US is spent in transportation. So if we can produce locally, on demand, the hardware when you need it without having to stock it, you would be better. And how are we going to be doing that? Well, we're going to use the printer technologies that exist, and also the 3D printing technologies that we are creating. Like I mentioned some of them in my talk, and some other people are doing that. And because of that, we're going to be able to create all kinds of very neat structure in the nano, micro, and mesoscale, and you can put them together to really do something quite complex. So instead, a lot of people are thinking of, can we use 3D printing to supplant injection molding? And well, I think that's an interesting question, but I think there's a far better idea, and it's like, can I print your cell phone in one seat? Can I print a car without assembly? And everything that I described really goes along the lines of making complex hardware that is multi-material, where these different parts are interfaced in a way that is efficient and that creates great hardware. And with that, well, I finished my talk. Thank you for your attention, and I'm open to questions.
There is only left time for one or two questions. If you want to make some questions to Dr. Luis Fernando Velázquez, please open your microphones. If you don't feel comfortable with your English, you can write it in the chat.
Can I make a small question?
Yeah.
Oh, perfect. So, right, I got a few experience using 3D printing, especially 3D bioprinting, and something that I found slightly difficult is dealing with multi-extrusion due to the lag time between one extruder and another, like one syringe and another. So, is there any way or any kind of process in which I can actually overcome that problem? Because, for example, when I'm printing something, some materials will need some keyring, and I cannot just like lose a lot of time between changing between syringes. And I may think that that's something that will be similar to other kind of technologies. Do you present? Yeah.
No, that's a great question and a great point. Like the problem is that a lot of people that work in multi-material, so the vendors that make multi-material printers haven't really thought things through, and they are obsessed with creating things of multiple colors, which I think it's really a missed opportunity, because people are not going to adopt printing because they can make in color. It's because they can make these different materials. And anyhow, to the short answer to what you say is, right now the way you do, so assuming the printer has multiple heads, because if you have one, there's no way to go around it. You need to swap the syringes, right? But the way you do it right now is to create dummy structures to make sure that the different materials are being supplied as wanted. And if instead of producing these dummy structures, how the thing should be done, well, the hardware should be developed in a way that it can tell whether it's flowing. So the reality is like what you describe it, the bioprinter is called direct in writing. It's one of the technologies. It's kind of extrusion, but you don't have to heat up necessarily the feedstock. And those things are that operate in open loop. So the printer actually doesn't know if the stuff is flowing. So if you were able to make hardware that actually knows when it's flowing and has valves and sensors and all that, which we're not talking about like Nobel Prize materials. Like it's something that would be fairly feasible. Then the problems that you're describing shouldn't take place. But what we do is basically we create dummy structures so that we know that when it's printing our device, it's actually doing it right.
Thank you.
Thank you so much, Dr. Luis Fernando Velázquez, for your speaking. So please, we're going to receive the next speaker. Thank you a lot for your speak.
Well, thank you, everybody. Have a good rest of day. So I understand you're having an event. I wish you having a best time. Like, unfortunately, we couldn't travel because of the pandemic, as you may infer. But hopefully we can meet in the future. Okay, so keep up the good work, and I hope to see you in a future opportunity. Okay, bye.
Thank you so much.
Thank you.
Thank you so much.